Hello, everyone, and welcome to fourth grade science. Today, we're going to discuss black holes. This entire term, we have discussed everything that has to do with space. We have seen the solar system, we have seen stars, we have seen astronauts, how far we have developed our technology to get to the moon, to Jupiter, to send rovers to Mars. So today, we're going to discuss the darkest objects in our entire galaxy, maybe in the entire universe, which are black holes. First, what are they? A black hole is a very dense object in space. The gravitational pull of a black hole is so strong that nothing can escape it, not even light. Okay, we have our planets, we have stars, we have asteroids. All of those objects in space, they have a gravitational pull, okay? The gravitational pull, sorry if there's a noise in the background. The gravitational pull of a planet or any object is how they can attract objects that are smaller than them because of their own gravity. Okay, the reason why we can stand on our own 2 feet on Earth is because the gravitational pull of Earth is pulling us down. Okay, the reason why we can jump on the moon is because the gravitational pull of the moon is not as strong as the one we have on Earth. So black holes have such a strong gravitational pull, they can pull everything that is surrounding them, even light. So where do they come from? They did not just pop in the middle of space. Black holes originate from stars. Okay, it's ironic how the darkest object in space come from the brightest objects in space. Most black holes, regardless of their size, are born when a giant star runs out of energy. Okay, we have several stars in our galaxy. There are thousands of billions of stars in our entire universe. We cannot count them. There's no way we can do that. We don't even know how many galaxies we have in our universe, much less how many stars are in our own galaxy or the entire universe. So stars can change from size to size. For example, our sun is not that big of a star. There are giant stars, hypergiants in our galaxies. And depending on how big they are, they can create a black hole. So, whoops, I returned. Okay. Let's go back. Before we discuss how we obtain black holes from the stars, we must know where stars come from. We discussed this in our class of the Big Bang Theory. If you recall, we discussed that stars come from nebulas. Every star is born from a nebula, a cloud made of space dust and gas. Not all of this material ends up as part of a star. The remaining dust can become planets, asteroids, or comets, or they may remain as dust. Gravity pushes these particles of the nebula together, forming the beginning of a star. So let's imagine we have this huge cloud of dust and space dust, okay? It's not something that we could see from Earth. But sometimes these particles start getting closer and closer until they make a small mass of solid rock. That solid rock can become an asteroid, it can become a planet, or in some cases, stars. Sometimes they don't become anything at all. They just remain floating around in space until they are attracted to something else. So when a star is formed, it's almost the same as a planet. It has a core, a center in which the entire energy is concentrated. So the core of the star is full of different gases that work as fuel. Okay, remember that the word fuel means something that gives energy. For example, our cars need gasoline, which works as fuel for us to drive around the town. These gases are working against one another, creating energy to keep the star burning bright. The bigger the star is, the more energy is needed to keep it burning. Stars that are great in size tend to have shorter lifespans than those of smaller size. Let's think about stars as huge machines, right? When we have a huge machine, we need a lot of energy to make it work. We cannot use just a couple of batteries and call it a day. No, we need fuel, we need gasoline, we need anything that will make the machine work. The bigger the machine is, the more energy is going to be needed for it to work properly. So we are going to use more materials to make it work. In the case of huge stars, they need a lot of energy to live for a long time. But sometimes those stars do not have enough energy. So even if they burn very bright and they are incredibly big, they will not last long because they do not have enough fuel for them to keep burning, okay? When the star stops burning, there are two things that might happen regarding, depending on how big the star is. So, talking about the size of the stars, can you guess which little star is that one? We have here in our entire slide, we have one red, very small dot that has no name. That one is a very important star. If you want to, you can pause the video right now, wait and try to guess which type of star is that one. If you have not guessed it yet, that star is our sun. Our sun is actually a very small star. It's big enough to pull the 8 planets that make up our entire solar system, but it's not big enough to be considered a giant star. Next to it is Sirius. Sirius is a little bit bigger. It's not considered a hypergiant, but it's sure bigger than our Earth and our sun, sorry. We also have Arcturus and our big fellow Betelgeuse. Betelgeuse is one of the hypergiants that are in this galaxy, okay? In the next slide, you will find a short link to a video. I will not show it throughout this video. So please, if you want to stop our video right now and you want to click on that link, you may. The slides, the whole presentation is in Academia. You can download it from files. In this video, you will be able to see a more exact scale of how our sun is compared in size with other stars. It's very cool. I suggest you stop our video, click it, and then come back. Now, what happens when a star dies? Depends. First, we have low mass stars. With no energy left to use, the star will collapse onto itself. It will crumble and become stardust and gas once again, which is what we know as a nebula, or in most cases, what is known as a white dwarf. A white dwarf is a star that is not shining anymore. It becomes a very cold piece of rock that is going to float around in space and eventually disintegrate. Then we have our high mass star, Betelgeuse, the one that we saw 2 slides before. It's one high mass star. Once a high mass star runs out of fuel, it will collapse into itself, creating an abnormal amount of energy. This explosion of energy is known as a supernova. Now, that word sounds pretty weird, super something. So let's check what it is. A supernova is the most violent and energetic phenomenon in the universe, a bright explosion of energy and stardust. These titanic explosions release an unimaginable amount of energy. For a period of days or weeks, a supernova may burn brighter than the entire galaxy. Okay, so we cannot control energy, okay? We cannot create it. We cannot erase it from existence, but we can transform it from one thing to another. When the star collapses, when a high mass star collapses, there's a huge release of energy, and that looks like an explosion. These are incredibly big. I cannot tell you how big it is, and just can tell you that it's impossible to imagine. And depending on how big the star was and how close it is, we can see it burning for days, for weeks, and it may burn brighter than the entire galaxy. So for example, here's a GIF showing us a small glimpse of what we imagine a supernova looking like. This is what we would see from Earth if there was a supernova close enough for us to see it, but it would illuminate the entire planet, okay? We would not be, it would not care if it was day, night, whatever. It will burn brighter than our own sun, maybe even our galaxy. So it would be a spectacle. Thankfully, and a little bit sadly, thankfully we can not see a supernova from Earth because all the stars that may be dying are too far away from us for us to see it. I'm thankful for that because those types of explosion of energies might affect our planets. It could even destroy one. But sadly, I think that it would be an amazing thing to watch in our lives. So we win, we lose sometimes. Then, the black hole is a plausible result of a supernova. A black hole appears when an extraordinary amount of matter is concentrated into a tiny space. So when the supernova explodes, sometimes it sucks onto itself and becomes an amount of matter very, very concentrated into a very tiny space, and it pokes a hole into reality. So here we have what we would think a black hole looks like. We have not seen a black hole in person using telescopes until 2019 when they took the first picture of a black hole. I will show you later. Why? Because black holes are so dark, they are actually invisible to any of our telescopes. The reason why we can find them is because we can see how they act, how everything around it reacts to the black hole. So, contrary to common belief, black holes do not suck like a vacuum cleaner. We see all of those movies in which we have this huge black ball sucking everything around it, just absorbing it. But that's not how it works. They actually physically tear apart the atomic structure of anything that has been trapped in its event horizon. We will discuss what the event horizon is in a second. But it practically breaks it apart into tiny little pieces and then absorb those tiny pieces. It does not grab it completely. So, for example, this is what people think happens. Here we have a moon, an asteroid, and a planet. So, this is not what happens. They don't get closer to the black hole and get sucked. What happens is that, let us bring them back. Here we have our subjects again. They disintegrate little by little until they become nothing. And that matter is absorbed by the black hole. Wow. So we have the event horizon. The event horizon is an imaginary line that marks the outer border of our black hole. Once an object crosses the event horizon, there is nothing that can turn back, okay? No escaping from this massive force. So let's pretend that in the middle of this image, we have a black hole. All of those lines surrounding it are what we call the event horizon. Once we cross it, there's no turning back. The gravitational pull of that black hole has already grabbed a hold onto us, and we cannot escape it because we are not fast enough to get out of this trouble. A black hole's gravity or attractive force is so strong that it pulls anything that gets too close. It can even swallow entire stars. Nothing can move fast enough to escape a black hole's gravity. This includes light, the fastest thing in the universe. Okay, that's why we say that nothing can escape it. As far as we know, light is the fastest thing in the universe. In fact, when we try to measure how long would it take us to get from one planet into another, we can say 100 light years. Because light, since it's moving so fast, we can say that's the velocity of it. But since light cannot escape black holes and there's no way that we can move at the speed of light, there's no chance, no matter how much technology we develop, that we can escape black hole. Because even if we manage somehow to make a machine or a contraption that would take us as fast as light itself, our body would not sustain that stress. And we would probably die even if we just got 1 second at light speed. So, light is not the only thing that behaves really weird close to a black hole. Time also gets all jumbled up. So, here we have an example that I took from one of the books of science that we have at school. The intense gravity near a black hole makes time behave in strange ways. If an astronaut left his spacecraft to explore a black hole up close, he'd see the hands on his watch ticking at a normal speed. But if anyone back on the spacecraft could observe the astronauts watch from far away, they had seen its hands slow down as the spacewalker got closer to the black hole. When the spacewalker returned to the spaceship after an hour-long spacewalk, years would have passed by for those aboard the spacecraft. Okay, see? So let's pretend that my hand is the black hole, and this one is going to be our spacewalker. The closer he gets, the weirdest the time is going to act. So even if he were 2 seconds inside of the black hole, many weeks could have been happening to anyone who is inside of the spacecraft far away from the black hole. See, nothing makes sense because the gravity pulls even time in the case of black holes. Okay, this one I took it from National Geographic. There's a couple of links at the end of the presentation that you can click on it if you would like to know a bit more about it. Someday humans might be able to use black holes to time travel forward. An astronaut could take a short trip near a black hole and return to Earth after years, decades, or even centuries had passed there. So in our previous slide, we discussed that the time inside of a black hole occurs very slow in comparison to the time out of it. So we could travel forward in time if we spent like 5 minutes inside of a black hole and then got back to Earth. Maybe years could have passed by. But since it happens slower in here and faster outside, there's no way that we can travel back in time. A black hole time machine could allow an astronaut to find out what the world will be like in the future. But going back in time, that's a different challenge altogether, okay? Keep that in mind. Here is a picture of a black hole. Remember how I said it's the darkest object in the entire universe and they are practically invisible to us? Well, in 2019, a group of scientists from NASA decided to build a machine that would try to capture what a black hole looks like. What we see here is a black hole in the center and the light around it, that's the light trying to escape the event horizon. It wasn't until 2019 that astronomers were able to take the first picture of a black hole. Located at the heart of a distant galaxy called M87 in the Virgo Galaxy Cluster, the black hole measures 40 billion kilometers across. It's 3.3 million times the size of the Earth. Thankfully, that guy is pretty far away because as we discussed, the bigger an object is, the bigger the gravitation, the stronger its gravitational force is going to be. So, it's in another galaxy, very far away from us, and that's the reason why we're not in danger. But if that object were to get closer to us, we would have no chance of escaping it because it's 3.3 million times bigger than our entire planet. There's no escaping it. So thankfully, super far away. There's no homework today. I hope you enjoyed today's class. In here, you have a series of links that I use as a source of information. We have YouTube videos by NASA. We have YouTube videos by National Geographic. And we have linked to Space Magazine, which is very acclaimed due to its exploring of space, okay? You can link any of these links if you want to find out more information regarding black holes in space. And I hope you have a wonderful weekend. So see you guys. And bye.